We begin chapter 12 by discussing vector-valued functions, and we're going to first remind ourselves what parametric equations are. So definition, if f, g, and h are three well-behaved functions, then the parametric equations, as stated here, x, y, and z, generate a curve in three space that's traced in a specific direction. That direction is called the orientation or the direction of increasing parameter. And the curve together with its orientation is called the graph of the parametric equations or the parametric curve. So we've already seen these and are familiar with parametric equations in three space. In particular, in 11.5, we discussed parametric equations of lines, and we also discussed that of planes in 11.6. Before we dive in too deep, we have a very important example that's going to crop up multiple times throughout this section and in later sections. And it's the parametric equations of the form x equals a cosine t, y equals a sine t, and z equals t. Now, let's take a close look at this. If we consider just these first two equations, x equals a cosine and y equals a sine, those should look familiar. So those two equations in two dimensions forms a circle of radius a, very much like the unit circle where x is cosine of theta and y is sine of theta. That weight in front of the sine and cosine is 1 because we're talking about a unit circle, that is a circle with radius 1. So this a right here just denotes the radius of the circle in two dimensions. Now that we add on this third dimension here, z equals t, what that is going to do is instead of having a flat circle, we're still going to have a circle, but it's going to move up as t increases. So you can think of this as a helix, or you can think of the classic toy Slinky. It's going to be a helix wrapped around a cylinder of radius a. So let's take a look at this. What I'm going to do first is I'm just going to mark on my x and y axes a distance a in both directions. And then let me just sketch that circle in the xy plane. And then I'm just going to extend this upwards so that we have this guiding cylinder here. All right, and so now let's pick some various values of t so that we can plot a few points and see this helix begin to wrap around this cylinder. So let's start at t equals 0. If t equals 0, then x is a cosine of 0, or in other words, a. Y is 0, and z is 0. So we have the point a, 0, 0. So I'm going to plot that here in red so that it stands out. Let's find some other values of t. Let's start with pi over 2. So in this case, our point x, y, z is going to be, cosine is now going to give us 0, sine is going to give us 1, and z is just t, so pi over 2. So let's mark out pi over 2 here on the z-axis. And let's plot our point right up here. So far, we have gone in this direction. Let's find just at least one more point at t equals pi so that we can see this wrapping around. So our xyz coordinate point becomes, cosine of pi is going to be a -1, so I get negative a, sine zeros out, and t is z. So now we're along the negative x-axis and we're up pi. So I'll denote pi up here, and we're on the back side of the cylinder. So it's kind of hard to express that when you're plotting in two dimensions, but we're somewhere back here. So we can continue this, and what's going to happen is we're going to continue to wrap around this cylinder. All right, so we can see the helix growing upward as t increases in this case. All right, so just keep this in mind. When you see that two of your parametric equations involve a sine and a cosine, and the other value is just growing with t, that should indicate that you're working with some kind of a helical structure. All right, so the name of this section is an introduction to vector valued functions. And so we say that a function r, which can also be expressed as r of t, that produces a vector is a vector valued function. So what we're inputting is a parameter value t, we're outputting a vector. So we have a definition here. If r of t is a vector valued function in 3 space, then for each allowable value of t, the vector r can be expressed in terms of components. And so what we're seeing here is those individual parametric equations, x of t, y of t, and z of t, inside our vector valued function. And then as always, we can write it in the ijk notation just as well. Those individual functions are called component functions or just components just as well. So whenever we're working with functions, the first thing we would like to know is what is the domain of that function. So when we're working with a vector valued function, all we're going to do is we're going to look at the domain of each individual parametric function or component function, and then we want to take the intersection of all the domains. That is, what values of t that are most restricted make it so that all of the component functions are defined on that domain. So let's jump right into an example here. We want to find the domain of this vector valued function, and we also want to find the value of r at the given t0 value. So first, let's talk about the domain. We're going to look at each of these functions individually. The cosine of pi t function is defined for all real values. So any t value will work. When I look at the natural log function, I know that t is only defined for positive values. Lastly, when I look at the square root of t minus 2, I know that t minus 2 needs to be greater than or equal to 0. So in other words, t must be greater than or equal to 2. So now I look at all 3 of these domains and I decide what t values would fit into all 3 of those domains. And as it turns out, this last piece is the most restrictive and still satisfies the other 2 domains. So we say that the domain of our vectored value function r of t is either t greater than or equal to 2, or you can express it as close to all the way up to infinity. So this is the domain of our function. Lastly, we would like to evaluate our vector valued function at the given t value, in this case 3. So we have cosine of 3 pi, negative natural log of 3, and the square root of 3 minus 2. So cosine of 3 pi is going to output negative 1. Can't do much here with negative natural log of 3. And then, of course, the last one is the square root of 1, or 1. So we're outputting the vector negative 1, negative natural log 3, and 1. All right, so we understand domains as well as how to evaluate vector valued functions. We would like to better understand the graphs that these vector valued functions output. So we have that definition. If r of t is a vector valued function in 2 or 3 space, then we define the graph of r of t to be the parametric curve described by the component functions for r of t. So the graph is exactly what you think it is. Let's take a look at some brief examples here. Describe the graph of the equation. So we're not actually graphing it, we just want to describe it. So looking at number 11, we have the following component functions. We have x of t is 2t, y of t is negative 3, and z of t is 1 plus 3t. So when we look at it in this way, we recognize this to just be a line. Not a lime, a line. And so you can refer back to section 11.5 when we discuss parametric equations of lines in 3 space. We also did lines in 2 space. And so this is going to be a line. And let me be a little bit more specific. Since we have a constant component function y equals -3, that means that all of our y coordinates are -3. In other words, this line is going to lie in the plane y equals -3. So this is a line in the plane y equals -3, containing the point 0, -3, 1, and parallel to the vector 2, 0, 3. So again, all I'm doing is I'm pulling off the components of the t terms to get the vector and pulling off the constant values to find a point on that line. So this accurately describes the graph of that vector valued function. Similarly, we can take a look at 13. Our component functions here are x of t equals 2 cosine t, y of t is -3 sine of t, and z of t equals 1. All right, so what we have here is, yet again, a constant z value. That means that whatever this graph is lies in the plane z equals 1. Now this one isn't quite as obvious because we have sines and cosines here. So what I'm going to do is I am going to solve for sine and cosine. So what I can do here is, let me just think of x of t as x and y of t as y. So I'm going to say that cosine of t is x over 2, and similarly sine of t is -y over 3. Now recall the Pythagorean identity that says that sine squared t plus cosine squared t equals 1. So if I square both these sine and cosine expressions, what I get is y squared over 9 plus x squared over 4 equals 1. So I can now identify this as an ellipse that is elongated in the y direction. So this is an ellipse in the plane z equals 1, and this is centered at 0, 0, 1. We don't have any shifts in x or y, and z is holding still at 1. All right, let's look at a couple more problems here. Consider the following problem. Find the slope of the line in two space that is represented by the vector equation r equals 1 minus 2t I hat minus 2 minus 3t j hat. All right, so what we're going to do is, if we're talking about a slope of a line, we want to find the derivative, right? And so I'm going to express these in terms of the parametric functions x of t and y of t. And I'm going to distribute that negative right here. So now let's find each of those individual derivatives. So dx dt is a -2, and dy dt is a +3. And then if you'll recall from when we learned about parametric equations, the derivative dy dx is dy dt divided by dx dt. And so what we get here is a -3/2. So the slope of this line is -3/2 units. Part B of this says find the coordinates the coordinates of the point where that line R intersects the XZ plane. So what do we know about all points on the XZ plane? The XZ plane has the main characteristic that all points in it have a y coordinate of 0. So if I want to find where this line R intersects the XZ plane, then what I'm going to do is I'm going to take this y of t function and I'm going to equate it to 0. And that will give me the time parameter t at which this line intersects that plane. So set y of t equal to 0, and I get 1 minus 2t equals 0. And so I conclude that t equals 1/2. So now I know the exact moment in time when this three-dimensional line intersects the xz plane. But remember, I want to find the coordinates of the point at which this intersection takes place. So I certainly know that y has to equal 0. What does x and z equal? All right, so all we're going to do is we're going to evaluate the x component function at 1/2. So that's 2 plus 1/2, or in other words, 5/2. And I'm going to do the same with the z component function, 3 times 1/2, or 3/2. So my point here is 5/2, 0, 3/2. This is my point of intersection. We end this section by taking a look at some graphing problems. So we want to sketch the graph of r of t, and this is important. Be sure to show the direction of increasing t. In other words, find the orientation. All right, so let's take a look at 21. We're going to start out easy. We have a constant function x of t equals 2 and y of t equals t. So if you want, you could plug in some values for t, and then you could find the xy coordinate points. For example, let's start with 0. X is always 2, y is going to be 0. What about if t equals 1? Then x is 2, y is 1. And we can keep playing this game. And the reality is the x coordinate is always staying the same and the y coordinate is just changing with t. So what we see is a vertical line here, and then just indicate the orientation. As t increases, the line moves upward. So our orientation is upward here. All right, not too bad. Let's take a look at 23 now. Quite a bit more complicated here. Let's zero in on those x and y component functions. So my x component function is 1 plus cosine of t, and my y component function is 3 minus sine of t. We're going to use the same approach that we used earlier with that ellipse, in that we would like to solve for sine and cosine and use the Pythagorean identity. So I'm going to just equate these to x and y. We'll omit that t notation here. And if I solve for cosine, I get x minus 1. If I solve for sine, I get y minus 3. So now, using the fact that cosine squared plus sine squared equals 1, I conclude x minus 1 squared plus y minus 3 squared equals 1. All right, and so from here, what I want to do, oops, and I just noticed I have a sign error. This would be a negative y and a positive 3, so do please correct that. But however, when I square it, of course, that negative is irrelevant. So I can now switch it back to y minus 3 if I choose. All right, so we recognize this to be a circle with radius 1 and center at 1, 3. So that center has just been shifted. Let's go ahead and sketch this. I want to go over 1 and up 3. Here's the center. The circle is going out radius 1. Now the only thing we're missing is the orientation of this parametric curve. And so we need to identify in which direction are we moving. So let's just do 2 individual values of t. So what happens when t equals 0? Well, then my xy point becomes the following. X is 1 plus cosine of 0, that's 2. And y is 3 minus sine of 0, which is 3. So we're starting at 2, 3, which is this point right here. So now the question is, are we going clockwise or counterclockwise? At this moment, we don't know. So let's plug in t equals pi over 2. So in this case, our xy point becomes 1 plus cosine of pi over 2, which is going to be 0, so I get a 1 there. And 3 minus sine of pi over 2, that's 3 minus 1, which is 2. So our next point is down here. We actually went clockwise, and so we indicate that orientation appropriately. And the reason why this orientation is clockwise rather than counterclockwise is from this negative sign here in front of the sign. Had both cosine and sine been positive, then we would have gone our standard way around the circle, which is counterclockwise, but that negative in front of the sign changed our orientation. All right, we have one last example in these notes. And so our component functions here are x of t equals 2 cosine of t, y of t equals 2 sine of t, and z of t equals t. This should look familiar. We discussed this on the first page of the notes here. This is a helix with radius 2 because we're looking at those coefficients in front of the sine and cosine. So you can plot that accordingly. We want to start out 2 on the x-axis, and then we just continue to wrap around this imaginary cylinder, so on and so forth. And we're always moving upward. That's easy to see by looking at this z component. Z grows as t grows. And so if you want, you can go ahead and make this solid all the way through so that you can see that helix. Right, so this concludes our notes for section 12.1.